Hello and welcome back. It's time to explore one of the most fundamental principles of electrostatics, Coulomb's law. Imagine you have two small charged objects, maybe tiny balls, one positively charged and the other negatively charged. Even when they're not touching, they pull toward each other. Or, if both have the same charge, they push away. What's responsible for this invisible force? Coulomb's law gives us a mathematical expression for the force between 2 point charges. Coulomb's law states, the electrostatic force of attraction or repulsion between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Mathematically, the magnitude of the force is F equals 1 divided by 4 pi epsilon naught multiplied by Q1 times Q2 divided by R squared. F is the magnitude of the electrostatic force. Q1 and Q2 are the two charges. R is the distance between them. Epsilon naught is the permittivity of free space. Coulomb's law applies to both attractive and repulsive forces. If the charges are like, both positive or both negative, the force is repulsive. If the charges are unlike, one positive, one negative, the force is attractive. And remember, this force acts along the straight line joining the two charges. This law is valid only when charges are point-like, small compared to distance. They are stationary electrostatics. The medium is vacuum or air. We've already seen Coulomb's law in scalar form, but force isn't just a number, it's a vector. That means it has both magnitude and direction. So, to fully describe the electric force between two charges, we need its vector form. This vector version becomes extremely useful when charges are placed in 2 or 3 dimensions, and especially when we deal with multiple charges in a system. Let's consider 2 point charges. The first charge, Q1, is located at position vector R1. The second charge, Q2, is located at position vector R2. To find the direction of force, we define the displacement vector from Q1 to Q2 as R vector equals R2 minus R1. This R vector tells us how far and in which direction Q2 is from Q1. Now here's the full vector form of Coulomb's law. F21 vector equals 1 divided by 4 pi epsilon naught multiplied by Q1 times Q2 divided by the cube of the magnitude of R vector multiplied by R vector. Let's break that down. The numerator has the product of the two charges, Q1 and Q2. The denominator has the cube of the distance between them, which we write as magnitude of R vector cubed. We also multiply by R vector to ensure the force has the correct direction. The constant 1 divided by 4 pi epsilon naught has a value of approximately 9 into 10 to the power 9 Newton meter squared per Coulomb squared. This formula gives us two things: the magnitude of the electric force and the direction, which is along the line joining the two charges. If both charges are positive or both negative, the force is repulsive, meaning they push each other away. If one charge is positive and the other is negative, the force isn't attractive. They pull toward each other. According to Newton's third law, the force on Q1 due to Q2 is F12 vector equals negative of F21 vector. This means that forces between two charges are always equal in strength, but opposite in direction. The vector form becomes especially important when charges are placed in different directions, such as charges on the x-axis and y-axis, charges in a triangle, or three-dimensional space. Instead of working with just magnitudes, we can use vector components, like x and y, to calculate the net force using vector addition, components and unit vectors. This prepares us to handle multiple charges, electric fields, and real-life systems in electrostatics. Let's wrap up this foundational topic with a recap. Coulomb's law quantifies the force between 2 point charges. The force is proportional to the product of charges and inversely proportional to square of distance. It can be attractive or repulsive and acts along the line joining the charges. In vector form, direction is handled with position vectors. For multiple charges, use the superposition principle to add forces vectorially.